80% of desks in MSB 260 have gum under them. So let's consider a binomial distribution with one trial. What is x? What is n? And what is p? Well, let's look at one single desk. We want to model with a binomial distribution, so we know we're going to need some number of trials and some probability of success on each trial. What a trial represents here is just walking up to a single desk, looking underneath it, touching underneath it, feeling for gum. We know that for each desk we walk up to, there's an 80% chance that there will be gum under the desk and a 20% chance that there is not gum under the desk. So the binomial random variable x is defined as the number of successes in n trials. So let's put that in the context of the problem. That would be the number of, how about we say, gummed desks out of one trial. Right, so we walk up to one of these gum desks and we look underneath, and there either could be gum. Well, we don't know if it's a gum desk. There could be gum. There might not be gum. So consider, in this problem, what are n and p? So n equals the number of trials, which is 1, and p is the probability of success on each trial, which is 0.8 or 80%. Also consider what the random variable x, what values it can actually take on. So in other words, we could walk up to this desk right now and see gum or no gum. So x could equal 0, or x could equal 1. What's the probability that x equals 0? Well, we know that that is the probability of failure. So that would have to equal 0.2. And we know the probability that x equals 1 equals the probability of success, which equals 80%. Now, what if we have two trials? So consider a binomial distribution here with two trials. So now we're concerned with the number of successes in two trials. Let's talk to two desks. Here they are. Go up to this desk. Here we go. We walk up to this desk. We're like, oh man, I wonder if there's gum underneath. Checking, checking, checking. Right? Is there going to be gum underneath? We can't say for sure, but we know there's a 0.8 chance that there would be gum under this desk. Now, independent of whether or not you found gum under this desk, I want you to go up to the second desk, the blue desk. Check to see if there's gum underneath there. What are the chances that there's gum underneath that blue desk? The answer is, it has to be 0.8. That's the idea with a binomial distribution, is we have this constant success probability no matter which number on the trial list we go to. Here we're just using two trials. All right, so consider, we have two desks, which x equals the number of desks that have gum out of 2. The random variable x, think about what it could take on here. So we could see 0, we could see 1, or we could see 2. Now the question is, what's the probability that we get 0? What's the probability we get 1? What's the probability we get 2? Right? Can you imagine if you walked up to those two desks in the room and neither had gum? Well, if you experience that situation, then you have 0 successes, because success is defined as having gum. Now imagine you walked up to both those desks, check the first one, check the second one, they both have gum underneath. You'd be in this situation. Now imagine you walked up to both desks and you checked underneath, and the orange desk had gum, but the blue desk didn't. Or the orange desk didn't and the blue did. That's with probability x equals 1. Well, let's look at 3 desks. Here we have 1 desk, here we have another desk, here we have another desk. So we have orange, blue, and red. Orange, blue, red. So x equals the number of desks that have gum out of, it's not 2, now we have 3 desks out of 3 desks. So consider what the random variable x could take on. It could take on the value of 0, could have 0 successes, 1, 2, or all 3. Now, what are the chances of x equaling 0? Well, what about the chances of x equaling 1? What about the chances of x equaling 2? What about the chances of x equaling 3? Well, let's first just consider how 0 could actually occur. So 0 means that none of the desks have gum, right? So orange, blue, red. So orange doesn't have gum. Failure. Blue, no, failure. How about probability x equals 1? How about the probability x equals 2? Well, those are going to take a bit more work, so let's come back to those. Let's get probability x equals 3. That means we have 3 successes in a row. Remember that random variable x represents the number of successes in 3 trials. Okay, so if exactly one of the desks has gum, it could be the orange one, and then the blue and red don't have any gum. The orange might not have any gum, and then the blue has gum, and then the red doesn't. Or perhaps the orange and blue are both gum-free, and then the red one has gum. Now consider the probability x equals 2. Perhaps the orange and the blue both have gum, and then the red, oh, no gum. Or perhaps we have check, x, check. Perhaps we have x, check, check. So how many different combinations do we have here? The answer is we have 8. We have 1 combination, 2, 3, 4, 5, 6, 7, 8. 8 different combinations. And we know the probability that x is 0 plus the probability x equals 1 plus probability x equals 2 plus the probability x equals 3 has to equal 1 because we have a valid probability distribution.